This is your friendly neighborhood physics teacher here, and we're going to go over your 1D motion free response on College Board. So, it says we have a cylindrical object, a can roll down an incline, as shown in figure 1. So this is a can rolling down the incline. The incline is slightly less than 1 meter in length. A group of students wants to determine the acceleration of the object while it's rolling down the incline. Students have access to the following equipment: stopwatch, a clock, a meter stick, a pair of clampers, which measure in length of 10 centimeters with a precision of 0.05 millimeters. Ooh. Assume that the object moves with a constant acceleration as it rolls down the incline. Write an equation that includes acceleration quantities that can be measured or obtained from measurements by using available equipment in the list. So there isn't going to be a lab question, but so besides the lab question, it might be saying, basically this is like a very mini version of derive the equation. If you remember, like 1D motion with these questions were at the beginning of the school year. So yeah. So let's think about what can be measured. So we know we can measure time. We're looking for acceleration. We can measure time, and we can measure the distance. A couple of things those are things we can measure. A couple of things that are just known, that we just need to know about this problem, is that your initial velocity is going to be 0. Because it states, let's see here, object, show the incline slightly less than 1 meter. Assume the object will stay at constant acceleration as it rolls down the incline. So we can assume that the initial velocity is 0 because you have to sit there and let it go and then roll. And we also can assume that our initial position is going to be 0. So now that's when we look at our equations. So your 1D motion formulas that are on your equation sheet, you have a Vx equals V x naught plus a xt. You have a x equals x naught plus v naught t plus 1/2 a xt squared. And you have a vx squared equals vx naught squared plus 2a x minus x naught. So now we have t. So it's okay. First, we're looking for acceleration. So acceleration's in all 3 of these. So we're good. We have measured t and we've measured distance. This one doesn't have distance. This one doesn't have time. So we're kind of left with that equation. Another thing that these have that we don't, if you look at all the stuff we know, we do not know our final position. We don't know our final velocity, so we can't use it. So we're left with our x equals x naught plus v naught t plus 1/2 a xt squared. If you just gave them that equation, you would get a point. But that's not it. This is technically not the true equation we would use because we know our knowns. Our knowns we have zeros, right? So plugging in the zeros, we would get that x equals 1/2 a xt squared. So that would be the equation you would want to submit. Now you would get a point for putting this one, but you want the full 2 points, you'd have to put this. So yeah. So if you notice, if you're looking on, so I've clipped out part A and part C because those are dealing with more, can't think what's called right now, lab stuff. But we're going to jump down to part D. So after rolling down the incline, the cylindrical object rolls across a horizontal surface as shown in figure 2. The object then hits a vertical wall and bounces off the wall with the same speed it had before hitting the wall. So what type of collision would that be? That would have been an elastic collision. Elastic. Because it hit and bounced off at the same velocity. So that's an elastic collision. Just information. Note that during the bounce, the object is in contact with the wall for a time interval that is very small, but not 0. On the dot below, which represents the object during the time it is in contact with the wall, draw an arrow showing the direction the object's acceleration after the bounce. So basically, which direction did the ball... This is a force equation without actually using the word force, since we technically haven't been taught yet, because it's at the beginning of the year. So which direction? Well, that ball is kind of... Can we move the ball? Okay, there we go. Put it here. So since it hits and bounces, so your acceleration after the bounce would go in that direction. Woohoo! So during the time that the object is in contact with a wall, is the magnitude of acceleration greater than or less than or the same as it was rolling down the ramp? So basically, it's asking, so rolling down the ramp is basically, so it's asking for, is the acceleration on the ramp the same or equal or greater than the acceleration after the collision? So now we know that acceleration equals our change velocity over time. For our ramp, our change velocity is just going to be basically our final velocity, because our initial velocity would just be 0, right? So it would look kind of like that. But our acceleration for the collision, our change velocity, we actually have a physical change velocity. Our final velocity, which would just be a negative version of our initial velocity. And so it ended up getting a negative 2v. And these v's will end up being the same, because it says after it rolls down the ramp, if I can get back to the picture, after it rolls down the ramp, then it hits the wall. So that initial velocity, that should be initial velocities. So these initial velocity and the final velocity is going to end up being the same, because this is what the velocity is going to hit at. And that was the velocity after it got done off the ramp. So those all end up being the same. So your acceleration during the collision is going to be greater, because you have a greater change in velocity. You have a greater change in velocity. Okay. So there we go. So this is the second question. I know a lot of people are asked me that when we had this. So just a good brief overview. An astronaut holds a rock 100 meters above the surface of planet X. The rock is then thrown upward with initial velocity of 15. As shown in the figure, the rock reaches the ground 10 seconds after it's thrown. The atmosphere of planet X is negligible effect on the rock when it's in free fall. So there's no it's not like thick or anything. So now, we had to think about 1D motion. As the ball goes up, the velocity at the top goes to 0. And then it comes back down. As long as it's at the same height, your velocities are going to be the same. Just one's going to be negative. So you have your initial velocity will end up equaling, no, I'm flipping it. So that's your initial velocity, that's your final velocity. Your final velocity will end up equaling the negative version of your initial velocity. So if your initial velocity is 15 meters per second, that means your final velocity is going to be a negative 15 meters per second. So determine the acceleration due to gravity of the rock when it's on planet X. So we're looking for AY. We know our initial velocity is 15 meters per second. We know, we actually know our final velocity during that little part. But it's saying it takes, it reaches the ground in 10 seconds. So we actually don't know our final velocity of the whole entire 10 seconds. So it takes 10 seconds to go from that. And we know that the rock is 15 above, or if not 15, 100 above. So we know that our distance is 100 meters. Now, we've already kind of stated that it's 15 here, it goes back up, comes back down, it's 15 there. We don't know the extra, upward. Okay. So there we go. So that's the information we have. Again, let's look at our equations. So again, we don't have final velocity at all because we don't know how fast it's going to be going right before it hits. We don't know that. So again, we're kind of stuck with this version of the equation. So we're just going to do y equals y naught plus v y naught t plus 1/2 a y t squared. Like I said, we just plug in what we got. So our y is 20, our initial will be 0. Our initial velocity is 15. We have 10 seconds. We're looking for our a, 10 seconds squared. So now we can just kind of simplify things out. Plus, we have 10 squared. Gives you 100, but then we have that 1/2 there, so we get a 50. We can't add those together because of this AI, so we got to bring this over. So we're left with a negative 50 equals 50 AY. Did I do that right? Oh, man, those negatives are trying to get me. So our final needs to be negative because it's going down. Direction matters. Position's a negative. Since it's going down, our negative that has to be negative. Whew. I was like, that's not the right answer. Let's try that again, shall we? So we get 8,250. And then we divide by 50. Gotta watch out for your negatives. Gotta watch out for your negatives. So you get a negative 5 meters per second squared. So negatives will get you. Negatives will get you. Oh, there's doubles. I forgot to take away the doubles. Okay. Take away the doubles real quick. I don't know why it doubles when I copy and paste it over sometimes. There we go. So how does the speed of the rock when it reaches the ground, so at VD, so they're calling this VD, compare to the speed of the rock when it's thrown upward, VU. So instead of V naught, they're calling this VU. So you're just comparing. So we've already stated that it'll go to it'll go 15, it'll go up to 0, and then it'll be 15 here. If gravity is still pulling it down, it's still going to be increasing. As it's falling. So your VD should be greater than your VU. And the reasoning is basically that. So your VU, that's a UU. So again, you would put this in kind of like paragraph form. I'm just going to dot it out for you. So your VU is going to be the same after it goes up. So after it goes up, so then it still needs to fall. Still needs to fall the 100 meters, since your velocity and acceleration are going in the same direction. Then so since your velocity and acceleration are going in the same direction, it will increase. Something like that. Okay, so a student wants to know how the motion of the rock would be affected if it was thrown upward at 15 meters per second from a height of 100 meters above Earth's surface in a clear, concise paragraph length. Respond that may also contain figures and or responses can contain figures or equations. Explain how the motion of the rock on the Earth will be different from the motion on planet X in terms of the maximum height above the ground, the speed at which it reaches the ground, and the time at which its free fall, and its acceleration due to gravity. So again, you're going to put this in paragraph form. I'm just going to dot it out for you. So right off the bat, you know that the acceleration on Earth is greater than your acceleration on planet X. Because your acceleration due to gravity on Earth is rounded to 10. It's 9.8, but we can round it to 10. And the acceleration on the planet X is 5. So we know that Earth has a greater acceleration. So if Earth has a greater acceleration, and the height stays the same and everything, we can look at our y equals vy naught t plus 1/2 a. So we can look at kind of like this equation. So that's staying the same. Well, here. So we don't have to deal with 2. So we're just trying to figure out the time right now. So let's look at this one. V equals v naught plus a t. So this is the same. This has increased. So if this is increased, or I'm wanting this to stay kind of relative, your time would have to decrease. And this is on Earth. So honestly, your time that it takes for an object to fall on Earth is going to be less than time it takes on planet X. You can mathematically look at it here, or you can just talk about that, well, the acceleration is greater, so it's going to fall faster, and so it's going to take less time to actually hit the ground. So you can say something like that. Now, in that same way, if you're talking about it being thrown up and then come back down, so that this distance here, if you're thinking about this distance here, it's not, on Earth, it's not going to go as high as on planet X. Again, it has more gravity pulling it down. So if you're looking at max height, so we can look at our V, oh, come on, right. So our V final squared equals V initial squared plus 2a delta y, just combining the two. So your final is going to be 0 because we're just going from there to there. It's 15. And then for planet Earth is 10. We can sit there and figure out the y, doing the same thing for planet X. So it'd be 0 equals 15 squared plus 2, 5 delta y. You can obviously see that your height, it's going to end up, because you're going to end up dividing, you're going to divide by a smaller number. This you're going to end up dividing by 20. This you're going to end up dividing by 10 from that 15 squared. So your delta y for planet X is, you're going to be able to go higher than you are for planet Earth. I think that's it. Hopefully that makes sense. If you have any questions, please ask. Have a wonderful day. Bye.